All right, let's. So you remember we started discussing the so-called first step analysis, and we already did one example. Let me go over another one. So this is also coming from your textbook. It's one of the problems, problem 4.4 on page 131. Okay. In this case, we are given a Markov chain whose transition probability matrix is known. So this is a chain on 4 states, and we have one-step transitions between these 4 states. Let me first write them. So it's like 1, 0, 0, 0. So if you are already in state 0, so there is no way to escape from there. So it's what we call an absorbing state. Right? From 1, you can go to state 0 with 0.1 probability. With 0.2, it comes back to itself. At 0.5 and 0.2, you can go to states 2 and 3. And on the third row, you have 0.1, 0.2, 0.6, and 0.1. And the last row reads like this. Okay? Right? Initially, we assume that this chain starts in state 1, right? So we are given a Markov chain X on state space 0, 1, 2, and 3, right? With one-step transition probability matrix. Anyway, let me just write it like this, given like this, right? What do we want to calculate? Okay, we would like to calculate the probability that the Markov chain never visits state 2 in this case, right? So state 2 is a very undesirable place. I don't know where, so you can come up with different stories, right? Initially you start in 1, right? And what exactly is going on? There are a finite number of states, right? And we can just draw a state transition diagram to see how the process is going to actually evolve over time, all right? So these are the states, right? I'm going to put an arc between 2 states if there is a positive probability of going from one to another, right? From 0, you can see that you can only come back to state 0, but otherwise you cannot really leave this state, right? Starting in 1, you can go any one of these states with positive probabilities, right? So we will then put arcs from 1 to 0 to itself, to state 2 and to state 3, right? And the others are actually also have full, right, rows with positive entries. So from 2, for example, then we know that in one step you can go to state 0, you can come back, or you can go to state 1 or 3, right? And similarly, if you start in state 3, you can go to state 0 in one step, right? Or to 1, or to state 2, or you can come back to state 3, right? Now when you look at this thing, you can see that there are a finite number of possibilities at each state, and eventually, right, you will leave this triangle and get absorbed to this one. And once you get there, you cannot get out of there, right? So we can show, but also I guess intuitively clear that with probability 1, right, the Markov chain is going to be absorbed, right, into state 0, right? And the question actually becomes like what? Along the way, right, the Markov chain, starting from state 1, going to state 0, what is the probability that it is never going to hit state 2, right? right? So for some sample patch, one will go eventually to 0 by going through state 2, and for some other sample patch, it is not going to go through the state as it is progressing toward these eternal states, right? 0 state here. Okay. How would you solve the problem? Any ideas? Now we can again use first step analysis, right? Starting in state 1, right? Though perhaps we need to just twist this original Markov chain or one-step transition probability to make life a little easier. Right? Any ideas? Have you seen such a thing before? Huh? No? Okay. What we are going to do is, actually we will modify first the one-step transition probability matrix. Right? Matrix. And we'll turn, right? Okay. Okay. Turn state 2 into an absorbing state first. Right? So once you get 2 with this original one-step transition probability, you can get out of it, right? We will just cancel these arcs. That goes out of this state, and then we'll, of course, the sum, the row sum should be 1, and we will make the probability of coming back to state 2 in one step 1, right? So in other words, we will have a state transition diagram almost the same as before, except, so we keep all these arcs, right? And when it comes to state 2, we will only keep this one and turn, well, this was originally, right, 0.6. We will make it 1, all right? Why do I do that? Now, I know that in the original chain, so obviously when you change the one-step transition probability, now you have another Markov chain, right? So you have a new Markov chain, let's denote it by x tilde, right? With now state, on the same state space, but with state transition diagram like this. Diagram like this, right? Now in the original problem, when you start in state 1, what you are really interested in, whether you ever hit state 2, right? Before you get, before you reach to state 0 or not. If you reach to state 0 before you get to state 2, right? You know that you will never be able to get state 2 anyway after that, right? So you only have to actually worry how the sample patch will progress over time until, for the first time, the state actually reaches state 0 or 2, right? In this case, when you, right? So this chain x tilde and this Markov chain, original Markov chain x, will actually have the same, exactly the same statistical properties until the first time either of these state reaches state 2 or 0, right? Because until this chain reaches state 2 or 0 for the first time, and this new Markov chain, until it reaches state 0 or 2, they will have actually the same behavior, right? Because it goes 3, comes back 1, or hits eventually and get absorbed to 0, or does this several times, right? It actually, this one, or this chain and that chain actually behave according to the same one-step transition probabilities, right? The only difference actually, the difference will arise at the very first time the chain enters into state 2, right? But then actually we know that the game is over. Then we can say that, okay, chain, right, this one also entered into the forbidden state, right? And then we can actually calculate the respective probabilities, right? So when you work like this, actually, if you just modify the problem like this, so this is going to be like a game which is being played until one of these target states being hit, and the probability that we want to calculate is the probability that game ends by first entering state 0 rather than state 2. If the game ends by first entering state 2 instead of state 0, that is equivalent to saying that actually the original Markov chain enters state 2 before it enters to state 0. Right? Did you get it? Huh? So here I would like to calculate what? The probability of going 0 without entering state 2. Right? That's equivalent to saying here the game is going to end. Eventually we know that it is going to end. But when it ends, we will be in state 0, not in state 2. Right? Aren't they equivalent? Markov chains are not equivalent. But until that random time, when, in this case, the chain enters 0 without getting into 2, is the same as for this chain, right, to get absorbed to state 0, but not by state 2. Huh? Can you see that? So they are different, but they behave along the same, well, exactly in this, according to the same statistical law, until the first time both of these states enter state 0 or 2 for the first time. Right? So they actually follow same path until one point, and then they start to move according to different rules. But actually what I was interested in anyway was the behavior of these chains, right, until that very first hitting time. Right? So when you look at the chain on the right hand side, right, we can again define by S the time when the game ends, right? Namely the first time this x tilde n process, right, enters state 0 or 2, right? So that's when the game ends, because if the Markov chain enters state 0 or 2, it is going to stay there forever according to this one, right? And I would like to calculate the probability, right? Want the probability that when this modified chain, when the game ends, the modified chain is going to be in state 0, starting initially in state 1, right? Right? What I was just telling you over there is this is the same as saying that the probability that original chain X gets absorbed into state 0 without ever going through, right? Okay. Going through the state, well, state 2. Starting again initially in state 1. Right? These two probabilities are the same. Right? This was what I want to calculate, and we will see that it is easier to calculate here. Right? The reason is actually, you know that eventually you will get to absorb into state 0 here, but there is no way to really keep track of what happened before you get into this state. Did you really go through this state 2 before, or did you not? It is difficult. It is difficult to really remember. But what I really do here is, if the chain were ever, the original chain were ever, if the original chain ever went through this state 2, I just turn this immediately into an absorbing state. Right? It is not going to be able to escape from there, but what is the good thing that does for me? Then I will remember that actually along the way the original Markov chain was going from 1 to 0, it really stopped by in this state. How do I remember that? I just cut the connections from the state to the outside world, right? And once I found out about that the chain has actually entered into state 2, I don't really care what happens after that, because that's actually what I want to know, that whether this event has happened or not. In that sense, right, until this time S, basically, both chains are going to have the same behavior, or the behavior that they will actually share will be enough for me to figure out those probabilities. Okay? Is it now clear? Right? Okay. So that's a typical trick that you sometimes have to play in order to solve problems. Right? There are a bunch of states. You know that the chain is eventually go somewhere. Right? You are asking to yourselves whether the chain. You are asking yourselves the probability that the chain will actually visit one of these interesting states before it going to this final destination. How do you do that? Well, if any state, any sample path ever gets through that chain, right, there is no way to really notice that in the original chain, but if you just cut the arcs going out of those states and turn that state into an absorbing state, right, if the chain ever gets to there, then you know that it is going to get trapped, and you will find the chain actually sitting over there for you to find out that it actually stopped by that state as it was going to the original terminal state. Right? That's the trick. Chains are different, but the quantities that I am going to be interested in are going to be the same for this too. Yeah.
Did you move to arc on node 3 itself?
3? Which one did I do that? Did I? No. I just forget it. I don't touch anything else, but I just turn this state 2 into an absorbing state. Absorbing just in the usual meaning. It absorbs whenever a particle gets in. It cannot go out of there. Right? Are we now comfortable with this idea? Okay, let's now. But the calculation then is going to be very similar to the example that we actually studied last night. What was that? So we are given now a game, right? You are starting initially in this state. Game ends as soon as the chain gets into one of these two states, and I am interested in the probability that I must have bet on the result that the game, when it ends, when the game ends, the chain is going to be in this state, right? So that's exactly this probability, right? Starting initially in this state, when the game ends, the chain is going to be in this a favorable state to me, right? And how do I calculate this? Again, we will just set up several linear equations, right? So this is actually one, the value of one function that you can define on the entire state space, like this one, right? So when the game ends, the chain is going to be in state 0, starting initially in state I being any one of these, well, okay, there are only 4 of them, right? Any one of these 4 states, right? And I would like to calculate this one, right? And I can figure out some of those numbers right away, like U0 and U2, right? What are they? Which one is 1? This is 1, right? U0. If you started already in state 0, then you know that the game immediately ends and you are in this desired advantageous state. So it is 1. And 0 otherwise, right? So these are sometimes called as the boundary conditions. Boundary conditions on the function that you are supposed to calculate, U function, right? So you already know 2 values that this function will take, or the 2 values of this function, on the values of this function on 2 elements of its domain, right? And then you still, but you are, no, not this one, right? I made a mistake. It is 1, right? So you are still interested in U1, right? And then we can now use first step analysis, right? To write an equation, for u1 in terms of the other known or unknown values of the same function. Starting initially in state 1, right? You know that the game does not end immediately because this is different than 0 or 2. So you know that you have to just let the chain go at least one more period forward, right? Starting from 1, it can go into either state 0 or state 1. No, either state 0 or state 2. Oh, it's funny. This is going to be easy. Or it's state 3. Yeah. Right? So otherwise, it is not going to be interesting. That's true. Right? With what probabilities each of these events happen? Right. We have to read them from here. You can just read them for me, I guess. Right? So it is going to go to state 0. 0 with probability 0.1. Once it gets to state 0, what is then going to happen? Yes, but just let us forget about the values first. Just the general principle was like what? Huh? But in general, so you are still saying like you are going to write 1 or u0, right? But how do we justify that you can actually forget about the past, right? And then you can think as if initially you started in state 0 rather than 1, and then you are trying to answer exactly the same question. Namely, the game is going to end eventually. When it ends, it is going to be, the chain is going to be in state 0, right? In order to be able to write u0 and just do what I just did, right? We use what? The Markov property, right? So we will remember this. So once you know that with probability 0.1, you will move from 1 to state 0. Once you get into state 0, now you know that you are in state 0. Do you need to know anything about the past in order to make any inferences about the future? No, you're not. You don't need to do that because what? Because the chain X tilde is itself a Markov process, right? It has Markov property, right? Then we will populate with numbers. That's what I want you to be aware of before you plug in any numbers. Right? Okay, so this is what happens if the chain moves to state 0, which happens with probability 0.1. Other possibilities are what? 0.2. With probability 0.2, the chain can go to state? State 1. It can come back to itself. Huh? Once it can come back to itself, again you know where you are, right? The Markov property lets you write here just what? The same value, but as if you start again in state 1, right? And finally, 0.5. Is it final? Probably not. No. Then you have u2 and 0.2 u3. Too many numbers. Why? Okay. So that's what we have for u1. And on the right-hand side, okay, you know what u0 is, you know what u2 is, but you don't, okay, u1, we can pull it to the left. We don't know what u3 is, then perhaps we also have to write then an equation for u3, just because you don't know what it is. Right? We need another equation. Here I have two unknowns. Right? Okay. For u3 we will play the same game. So starting initially in state 3, I know that the game doesn't end immediately. So I will just wait the chain to go for at least one more period. When you just let it go, with certain probabilities, it is going to move one of the states, and once you know in which state the chain goes in, Markov property kicks in. It says that, okay, I don't really care how you got there. I know that you are now here, and the problem is now the same for you, because the future event doesn't really change in this case, right? And then you will just argue as just the same way as we did before, right? So with what probabilities do we go to which states?
0.2.
Right. U0. And with probability,
0.2.
we may go to state 1, and starting from there on, right, I face the same problem, therefore I can write U1. So U3 turns into U1 with this probability, right? And plus, with 0.3, I guess, it becomes U3, and 0.3, with 0.3, the chain is going to move into state 4, and then starting from there, right, now we have this problem turns into finding the probability of getting it to state 0, starting initially in state 4, right? Am I right? What is 4?
2 and 3.
Yes, okay. 2 and 3. All right. So we are now safe, right? Okay, now we can now remember what the boundary conditions were, right? So these are the boundary conditions. These are just the equations that the function satisfy, right? So this is 1. So I can take this to the left, right? U2 equals 0, so this will disappear. This will disappear as well, right? So we can take this U3 to the left, right? And we also know that these are all 1s, right? And we can then write what? So if you move this to the left, you have 0.8 times U1 equals, you have 0.1, right? And plus 0.2 times U3, right? And if you move this last term to the left, then you have 0.7 times U3 equals 0.2 plus 0.2 times U1, right? Now, I have two equations in two unknowns, right? And U1 was in particular what I want to calculate, right? Here U1, if you divide by 0.8, you get what? 1 over 8, right? Plus 1 over 4 times U3, which is given by this after you divide by 0.7 both sides, right? If you divide by 0.7, you get 2 over 7 plus 2 over 7 times U1, for example, right? And then we can just simplify things. What do I get here from here? 1 over 8. And here I get 1 over 14, right? Plus, okay, 1 over 14 times U1. If I take this to the left, then I have 13 over 14 equals, right? How do I make them equal? So maybe I can, is it 56 what is common? Or more than that? I multiply with 7 and multiply this with 4. Huh? And you get 11 in the numerator, in the denominator you have 56. And therefore, what happened here? There is U1, right? U1 equals, then, well, okay, this will cancel this and we'll get 4 back, right? And this is like the 11 over 4 times 13, which is 52. Am I right? Okay. A weird number, but it's still a number between 0 and 1, right? That's how you find the probability that you don't go through the state 2 as you are going eventually to state 0, right? Do we have any questions? Right?
So,
yes?
can we say that if it starts on state 1, it exactly visits state 2 is 1 minus 11 over 52?
What do you think? If you start in state 2, there are two possibilities. Either it is going to go through state 2 or it doesn't.
It starts with state 1.
So, okay, it starts in state 1, so it is either going to go through state 2 or it does not go through state 2 as it eventually goes to state 0. There are two possibilities which basically cover all cases, right? So there are two events whose union give the entire sample space, therefore their probability should sum up to 1. The answer is yes, right? You are following me, right? So either you go to the state 2 or you don't. You calculate the probability that you don't, with this probability, you don't go to the state 2 as you are going to state 0. 1 minus this, of course, should give the other. Or otherwise, oh, yeah. U3 is something else, right?
So it goes through the same process it asks the question.
It doesn't really matter which part of the question you solve, right? But initially, if the question was set like that, of course, like it's more natural to formulate it like that, right? You would be looking then, perhaps you could have actually started with this probability. Right? Right? Now I defined another function starting initially in state 1. When the game is over, the chain is going to be in state 2 rather than 0. Right? Because if the auxiliary chain, right? This is an auxiliary chain. It is not the original one, but I just made up this chain just to help me answer the question here. If the auxiliary chain first enters here, right? That is equivalent in the original chain to saying that as it is going to state 2, it first entered into state 2. Right? Here, as I said before, I really didn't care what may happen after it leaves, after the original chain leaves the state 2. Right? But that's exactly the point. I'm interested in whether the original chain enters at all into the state 2 or not. Right? So, that's one way to answer the question. But as I said, if you solve this problem, you also have solved that other problem as well. So you don't really do any additional calculation. Because we know what? We know that with probability 1, right? When the game is over, this is going to be 0 or 2, starting initially in state 1 with probability 1. Because the game ends in either of these cases, right? So we know that this is going to happen for sure. And this is just the sum of these two probabilities of these two disjoint events. Right? Now you know the probability of one event, then just by subtracting it from 1, you will also know the probability of the other event happens. Right? Okay? All right? Okay. What else? This is also an interesting problem. I am just picking up different things where you can learn different tricks to solve problems of this sort. Right? This is problem 411 on page 132. Right? So in this case, we are given an urn. Right? An urn contains 2 red and 2 green balls. Right? And the balls are chosen at random, one by one, and removed from the urn. Right? And the selection procedure continues until all of the green balls have been removed from the urn. So you don't care actually what happens to red ones. Right? So there are 4 balls. 2 of them are green, 2 of them are red, and you pick at random, one at a time. And the game is over. In this case, both green balls are removed from the urn. Right? What we are interested in is the probability that a single red ball is still in the urn at the time that the last green ball is chosen. Huh? Right? So apparently the last green ball doesn't really want to be the last guy in the urn. Right? And we would like to know that there will be a green guy. Right? So the green ball is not going to feel lonely. Right? So that's the question. So what is it? So we have an urn, right? Right? And 2 of them are green and 2 of them are red, right? And we choose, we pick, right? A ball at a time at random. So all balls are equally likely to be picked up, right? And pick a ball at random, pick a ball at a time at random until both green balls are removed, right? And we would like to calculate the probability that, right, there will be exactly or at least one, a single. It says there will be a single red ball, right, left in the urn, right? After, when the game is over, let's put it like that, right? We know that the game is over as soon as you remove the second green ball, right? Do I have to write it like that? The after, when the game ends. Let me write it like this. When the game ends. Right? So that is what we want. Okay? So by now what did we learn? Your life is easy if you pick up the right Markov chain with the right state transition diagram or one-step transition probability, right? So we have to start with that first. So what would you say that the convenient Markov chain is going to be to solve this problem? What sort of information do you think you should actually keep track over time? Right, so this experiment is going one at a time. You pull the ball, you will want to know what? Right. How many green and red balls have remained in the urn? Right? That's great. Okay. So let's just define them by x sub n. Right. The number, right? Number of green and red balls, right? Left in the urn, right? After the nth ball is removed. Okay. So that's the piece of information I have to remember, right, at time, and in order to decide whether the game is has even ended or not, right? And when if the game is over, then I should then be able to say whether this event has really happened or not, right? Okay. This is a Markov chain because at any time, as you calculate the probability that you move from one configuration to another, you only need to know how many balls have remained in the urn because they determine the probability. With what probabilities you pick one of, whether you pick a green or red balls, right? And therefore, X, right? If you look at it like this, is a Markov chain on what kind of a state space? Two states, two tuples, perhaps. Okay. So we can just, then we will have IJs, kind of, right? So let's say that I keeps track of red balls, number of red balls, right? And J like the number of green balls, right? And now it is difficult to really list here, but rather let us just again construct the state transition diagram. So we will not only figure out what states are relevant, but also find out the transition probabilities at the same time. Okay, let us look at the state transition probabilities. I haven't yet formulated the problem. Namely, I didn't write what this thing corresponds to within the setup. That's going to be clearer if you just write down explicitly write down explicitly state transition diagram. There we will actually figure out which states are relevant for this problem, right? Transition, what does this mean? Okay, state transition diagram is enough. Okay. All right. So, initially, what is the configuration? You look at that thing? 2-2. So you have 2 red, 2 green, right? Let's just agree that, so this is the second one keeps track of the green balls. As we move to the right, let's say green balls are picked and removed, right? And as we move downwards, let's assume that the first component changes. Red balls are removed, right? So that we don't make mistakes, right? So when there are two, and when you move a ball, there are two possibilities. You must have either moved a green or a red ball, right? If you remove the red ball, then you will move from state 2-2 to state 2-1 in one step, right? And if you continue like this, then you will have 2-0, right? And do I further go from here? Because the game has already ended. Because you no longer have any green balls. According to this specification, it says, where does it say? Did I erase it or no? Okay. Yeah. Both green balls are removed. Right. Right. So this is then what? An absorbing state. Right? So there will be an arc like this. Right? And from 2-2, instead of, if you remove a red ball rather than a green, then you would have, the chain is going to move to state 1 and 2, right? If you remove one more red, then it's going to be 0, 2, right? Is this an absorbing state? No, because there are still green balls, so the game will continue. But you know that with now probability 1, you will always remove a green. So you know with probability 1, you will move from 0, 2 to 0, 1 state, and finally to 0, 0. But now, in this case, even the urn is empty. And what happens here? Well, there is one red and two green. So here we know what happens if you remove one red ball. And now we can just study what happens if you remove a green ball, right? Then this will move to state 1 and 1. And further goes to 1 and 0. And again, this is absorbing because no green balls are left, and according to the statement, right, the game is over. So I don't really worry about the other one. So this is also absorbing. This is, of course, absorbing, right? So I don't put any arcs here. But there may be transitions like this because there is still one green ball left. Until I remove it, the game is going to continue, right? Now I have such a state transition diagram, right? Let us also put the probabilities. Now, 2-2, right? Going from here, you must have selected green ball with what probability? 1/2, right? Or 2/4, right? And this is like what? You must have removed green ball 1/3, right? If this is 1/2, of course this has to be 1/2, even if you don't really think about it, right? Here, you have 2, you must have selected one of these 2 green balls out of 3. Right? And then therefore this is 1/3, right? This was 1/3, therefore this should be 2/3, 2/3, right? Here, 1 from each, then this can happen with equal probabilities, right? And we said this is going to happen with probability 1, this is going to happen with probability 1, right? Okay, so now I have a good understanding of what this Markov chain is about, right? But how can I now find this probability? Can I really use this to find that? Okay, give me the formulation. How would you formulate it? You have seen several examples by now.
Initial state is 2,
Yes?
you want to go to 1, 0.
This one. Yeah, this is the advantageous or desirable state, right? But the game can end in one of these 3 states, right? So how would you define, how would you just formulate the problem? You would first define what it means that the game is over, right? So this is the first time, minimum, the smallest n, yeah? So it is maybe more natural just to say that the first time, right, this chain x n enters to where? Now this is when the game ends, right? Exactly. There are 3 possibilities. Now this is not nice. So we will soon be using these states to enumerate or just label all these functions. Why don't we just give a simpler numbers as states? So let's call it this is state 1. Okay? And this is state 2. This is state 3. 4, 5, 6, 7, 8, and 9. Right? So instead of this, now we can just write, 1, 2, 3 through 9. Right? Now, it is now easier here to say that game is over if at the first time when the chain enters to one of these three states, namely 3 or 6 or 9. Right? Now we know that. Which one of them is desirable? It is this guy, right? And what is it, the probability that I want to calculate over there? When the game is over, right, at time s, you look at the state of the chain. Where is it? If it is in state 6, then you win. Therefore, you are interested in this winning probability. Starting initially in which state? 1. This is actually that one. The probability that you want to really calculate is actually this one. Right? Alright. So if you are patient and just go through carefully these steps, then the question is nothing. So if you look at this statement, it looks like there is a difficult, tricky combinatorial problem that you face, but it is actually not. Alright, so but in order to solve this one, I have to find several other probabilities at the same time. If you especially want to use a Markov property and therefore the first step analysis. Right? So in fact, okay, so this is what I want, right? But in fact, if I define by UI or denote by UI the probability that starting in the initial state I, 1, 2, 3, 9, what I want is U1, right? That's I1. That's what I want, right? Okay. So I have to figure out 9 numbers. But along the way, if it is easier to find the U1, of course, I don't really need to do anything more than that. But I suspect it is not going to be possible. Okay. So some of those UIs are easier to find than others, as before. They actually give us what we call, again, the boundary conditions. Right? You may not realize, actually, what we are doing here is actually we are setting up some differential equations. And then how do you solve the differential equations? You actually have to specify initial values or the boundary values, actually, in this case. Right? What we are finding is the boundary values first, and then there are actually differential equations that you solve. Well, does it really mean that you have differential equations in discrete time? Well, actually, the right word for that is the difference equation in this case. You don't realize, actually, what you are writing, but it is exactly what we are doing. In the first example, for example, here, right? So these are difference equations. These are analogs of the differential equations in continuous time. Right? Therefore, this term boundary condition is quite well chosen, actually, in that sense. So you have these difference equations that the unknown function is supposed to satisfy, and then you know the values of that function at the boundary outside of the world, and just you use the differential equations to calculate them. Anyway, you don't need to worry about too much about these things, but I was just trying to explain you why somebody would call the values that are the obvious values of a function the boundary conditions. That is the reason. So what are the boundary conditions? Well, I know exactly what exactly the value of U3 is, right? It is 0. Well, okay. I have also U, not 6, but 9, I guess. These are all zeros, right? And U6 equals 1, right? Now, rather than now writing blindly all these equations as before, like there are too many states, we can actually solve immediately some of them. What are they? Start from here. If you start with states closer to the boundary, you can figure out those values right there. For example, this one. If you start initially here, you know that with probability 1 you will move here, it is going to be 0 as well. How about this? Now, since this also equals 1 times U8, which we now know is 0, so this is 0. So all three are what? 0. So actually we can just write as well what? The last row starts with 7, I guess, right? U7, U8, are also zeros. What's going on? Okay, so let us just finish this exercise. And then we can perhaps look at this one, right? With, okay, is it the one that I can say something about? Yes, because I also know the boundary value here. I know the value of the function here. I know the value of the function here from the boundary condition, first line. So I can figure out the value here. What is that? U5 equals 1 over 2 times U6 plus 1 over 2 times U8, which are 1 and 0. So you have 1 over 2 left then, because this kills 1 over 2. There is 1 over 2 times 1 left. So what do I have then? U5 equals 1 over 2. Then you can perhaps tell me what U4 is. 1 over 3 times 0 plus 2 over 3 times 1 over 2. Right? So this is 1 over 3. And what else do I have to know? I have to find out this, right? I can't, this depends. 1 over 2 times something that I still don't know. So I better just first calculate this, right? What is this? U2. 1 over 3 times 0 plus 1 over, no, 2 over 3 times, what was it? 1 over 2? Okay. 1 over 3 as well. So actually, what is this? U2 equals to 1 over 3. You have similar calculation as well. Now, finally, we can find U1, which is with probability 1 over 2. You can go either to state 2, namely then you will multiply 1 over 2 times, right? U2 plus 1 over 2 times U4, and they both equal 1/3, right? 2 times 1/3 times 1 over 2 gives you 1/3, right? Then you get nervous, right? The 1 over 3, there were 3 possibilities. Does this have anything to do that you have actually, you have it 3 possibilities and then you ended up here? Most likely yes. Most likely yes, but it is really difficult to see why it is correct. Okay, let's give a break here, right? And 10-minute break.